here's the obligatory, all my students and recent grads on AI Ed projects. Some of them have actually graduated, and there's a lot of different ones I'll be talking about. Then I'm really excited by these collaborations, some of which are funded and one of which isn't yet, so wish us luck. One on middle school physics from DRK-12 NSF, and a brand new one with people in statistics education at the college level with collaborators at Penn State, and then a data set that I collaborated with Kathy Koenig on. She developed an inquiry-based curriculum for college physics. So unfortunately, I wanted to throw everything into this talk because I really like talking about this stuff. And I decided to try to break it up into 4 major pieces and get through the first 2 pretty quickly so I can get to the interesting new stuff. So I'll give you some background on these different projects and the different data sets and how small they are compared to NLP data sets, which is part of the motivation for some of the techniques that we use. Then I'll talk about a middle school roller coaster project that has essays and questions. And the first part of looking at this, the essays, we're actually using sort of a dictionary of pre-trained fixed vectors and then data structures and algorithms kind of approach rather than any kind of big neural network or anything. But then the later topics are using relation networks. I'm getting kind of interested in human in the loop kinds of questions. I think I've always been kind of interested in human machine interaction and how machines and humans are really different. And how do we put them together in a way that maximizes what they could do together? And I don't get into that too much, but I will talk about some work on human in the loop. And then finally, this later work that's looking at a kind of data set that's a little more structured than typically, and how we are incorporating contrastive learning. So the project on the middle school physics uses this web delivery environment that was just created. The person who works on it, Sadhana Bekar, has been doing this for a long time, scaffolding of science knowledge for middle school students. But it's the first time the whole thing is delivered through the web. And so what students go to is something where they can actually carry out their roller coaster simulations, where they do experiments and collect data, and then they answer questions, and then they're prompted to write an essay where they're reminded that there's like some main ideas of the whole curriculum that they should include in their essay. So here, what I'm showing is the first set of main ideas. The second set I won't go into, it just adds 2 more. But the idea is for them to get these down solid and then go on to add in the next 2. And so they can actually list the main ideas that they're supposed to get. And here I'm showing the 6 that they're supposed to get and be able to show evidence of knowledge of in their essays. And one of the questions that's a little bit more complicated, how did changes in PE and KE affect the total energy? And what does that tell you about the LCE? Well, that's hitting 3 of the main ideas. The student addresses 2 of them and only gets partial credit on this 0, 1, 2 scale, where 0 is way off the mark, nothing, no credit. 1 is partially there, 2 is you got it. Then in the essay, you can see I highlighted 2 sentences. That's what our tool is supposed to do, is in a kind of a checklist way, indicate to the student, did you get this idea? Did you get this next one? Did you get the other one? How many did you get? Which ones should you try to address in your revision? So that's that data set. Now I'm turning to this college student statistics data set, where here, instead of just a standalone question, that's a reasoning question with the answer, there's a scenario with 2 questions that go with it. And a lot of undergraduate education apparently uses this kind of questioning, and that's going to motivate one of our more complicated networks. So we get the scenario, we get the question prompts, we get the rubric, and we have examples of correct reference answers, partially correct reference answers, and incorrect reference answers. Now, the college physics lab reports have more complexity. The students do 4 kinds of experiments, series of experiments directed at learning something. Like the first one is about the pendulum. Then, after doing a bunch of experiments and answering some questions about those and submitting plots and so on, they have to write a full report where they have a lot of discussion. And they're supposed to, they get a rubric, for pendulum, it's 7 dimensions where they're supposed to be able to answer, these 7 different components. And so what we did with our data set to create this data set is we took the reports that had been written. We have 1,000 of the pendulum report, 1,000 in force and motion, and we knew the TAs didn't assess them reliably, right? It's a huge class, many sections. What we did was took the same rubric, expanded the scale from 1 to 3, but also zeros in there to be a 6-point scale, 0 to 5, where it's an assessment rubric only. So for each point on the scale, very precise objective criteria for does the student get 3 points or do they get 4 or do they get 5? And then this could serve as feedback because if the TAs could be encouraged to use this kind of rubric where they assess each dimension independently so that the total score is the sum, then the student would get specific feedback. Oh, on question 4 or item 4 in the rubric, I only got 3 points and I can see why. And so we have reliable grades attached with that. So here's the 4 data sets, and you can see we're going to try to make them publicly available. Some of them can't be made publicly available yet because they were originally collected without consent and so on. I just have an estimate of how much we're going to get from college students in statistics from partner institutions across the country because we're just starting that project. But you can see that, the size of the data sets, like maybe 2,000 essays that we can make public when we're done, and 9,000 questions that we can make public when we're done. We have 7,000 statistics questions or answers to 6 questions, but it's 7,000 items. We also have 7,000 more that haven't been assessed that we're going to assess human in the loop and so on. And then the lab reports are actually available, but they're small compared to the data sets we're used to in NLP. So now I'm turning to the second part of the talk, which is about how we assess the middle school essays. And I think I'll just see if I can squeeze in the time to give you a little historical background, which is way back when I was working on summarization at Columbia University with a bunch of people there. I worked with a PhD student at the time, Ani Nenkova, who's now at Penn, on how can we assess machine-generated summaries. And I turned to the literature on reading comprehension to get ideas. And one of the things I saw was that, God, they create these annotations that are just way too complex. But another thing I saw was that we need to have some way of getting importance of ideas. So this is based on something that goes back to 2003 and 4 that wasn't automated, a manual annotation method. Now it's fully automated. And this is the thing that uses computed vector dictionary done on a very high quality definitional corpus. And we've compared it with representations that are trained on different corpora, and it's very high quality. And I think that's because in a definitional sentence, every word in the sentence is sort of related to every other word in the sentence. But this shows the full pipeline, which is that there's some input. We have some reference texts written by experts. And we only need 4 or 5 to get what we want, which is not only what are the ideas, but what is their degree of importance, which I'll say something about in a moment. Then there's the set that we're going to evaluate. They both get pre-processed the same way. We use syntactic parsing of 2 types, merging information from dependency parsing and syntactic and constituency parsing to get full propositions that are tensed. And we get alternative decompositions of the same sentence. And then each clause is turned into a latent semantic vector. So we get our vectors from the reference text, and we get our vectors from the text to be evaluated. Then we have these 2 algorithms. EDUA is a restricted set partition algorithm that creates a pyramid, which is across our n reference texts, take the ideas in the first text and see how many of the other texts also mention that idea. So the maximum number of references that would mention that idea is just the maximum number of references. So we have weights on every idea from 5 to 1. And that's what this represents. So the few dark blue ellipses are the important ideas. So this is an emergent representation of importance of ideas. And then many, many in the long tail of, all these people also mention even though they're expert, they mention ideas that are not that important, but they help provide background. Then WMIN is the algorithm that assesses it. It's a greedy algorithm for weighted maximal independent set, and I'll say a little bit more about that. But first, I want to say, how do we get from this emergent notion of we have reference texts and the importance of the ideas just emerges to, well, we've got a curriculum. We know what the 6 main ideas are. Well, it's kind of, manual iteration over some high quality essays where we mostly get the kind of pyramid that we want. And what we want is the weight 5 ideas are all and only the 6 important ideas in the curriculum. But then we also have to have all these other ideas represented that are lower weight, because we're using cosine similarity to match student vectors to the content units. And if there's a lot of contributors to a content unit, like say 5, we take the average of the cosine similarity. And because students sometimes are sort of saying what they should be saying, you could have a sentence that kind of matches a high weight content unit, but not really. So it turns out we have to have a lot of the noisier content units that are lower weight to make sure that when we identify something as being high weight, the student really has pretty much said that complete idea. So that's a pyramid. And then here's the assessment. So maximal independent set. It's a set of vertices from a graph that are not connected to one another. So here's a little illustration on a star graph where all the little pale vertices are the ones that would be the maximal independent set. And so on the other side is a hypergraph. We adapted this algorithm to work on a hypergraph where each hypernode is one analysis of a sentence. So we have sentence 1, when the car leaves the top, it moves down because it has kinetic energy, 3/10 quadrats. So we've got, I'm just showing 2 of the alternative hypernodes for that sentence, S1.2 and S1.3. And the internal nodes are for each clausal unit, which could be 2 clauses or 1 clause. We can only pick one of those. We can't take the same sentence the student has written and analyze it 2 different ways to give them credit for it. We have to commit to one. That's what that first edge is. We pick one of those nodes, not both. Then each internal clause node is matched to a set, top K, of content units that it's got sufficient cosine similarity to. But notice that here we have content unit 5 occurring in both these hyper nodes. And it's got a little dashed edge. That's for, we cannot pick both of those. The content unit can't match both because we only want to give the student credit for getting that idea once. And we want it to be the best statement of that idea if we can. So that's the basic idea. And what we what WMIN tries to do is that there's a lot of little weight parameters that I won't go into. But we try to aim for giving the student the maximum credit that they can get. Question?
Yeah, I actually do have a question about this kind of evaluation. This is really a question about the way the rubrics work. So I have a sophomore in high school at the moment who's about to take an AP exam and has basically been coached by the teacher to take advantage of the fact that the rubrics are grading recall rather than precision. So if you don't know what year, I mean, this is an exaggeration, he was not told this, but if you don't know what year the Constitution was written in, make 3 sentences, or took effect in, you can say 1776, 1789, and 1865, and you'll get credit if anyone was right. Is that what's going on?
That could happen here. And actually middle school students are pretty repetitive. Because they sort of feel like, okay, I'll write a sentence. I'm not sure I like that one. Let me write it again. And then so they'll write it over and over again. But we're going to pick one sentence if any of them match one of the weight 5 content units, not all of them.
Right, so
and so they might.
To game the system.
It is, but they don't know that.
Except they're being coached.
Well, yeah, but these students don't know that yet. Okay. So, there's always, I mean, like you mentioned, somebody I was talking with today, I've actually had the notion of an arms race come up in several conversations. And that's what, we're involved in arms races of all kinds all the time. So I think what we have to depend on is that sometimes we get students who really just want to be able to learn and, forget the others, maybe, I don't know. Anyway, move on to the questions where we have our first relation network that's very simple, relational or relation network, either way. And so here I'm just trying to explain the motivation for it in kind of two ways. One is that we have multiple pieces of input text that we need to consider to assess a student's answer. The question prompt, the reference answer, and here it's actually a rubric, and the student's answer. And the color coding shows that, for certain kinds of aspects of the semantics of this, they're all three related, the green words. And for other things, it's like the question and the reference answer are more closely, have more overlap than with the student answer, and so on, all pairs. So in a sense, it's sort of like we want to get a representation of that whole thing that captures those interrelations. And that's this sort of conceptual motivation. But then there's this practical motivation. Like, let's say we use a big transformer model. It's going to have a lot of parameters, but relation networks are actually more efficient. And these data sets are often quite small. And in fact, the results I'm about to show you are using data augmentation with back translation, which I won't say any more about. But we actually encode the question, reference answer, and student answer with our favorite encoder, doesn't matter what. And then you learn an MLP, with an MLP, you learn a vector from that, and then you have another MLP that then you send to your output layer. So it's kind of simple. Here's our network where we have multiple vectors that we're going to create for each student answer because we have multiple reference answers. So for every reference answer, we have to create a vector. But then we've got all these vectors. What do we do with them? We have to fuse them together. And we could use a weighted average or something, but instead we learn a feature-wise fusion function to combine them. And then it gets sent off for the correctness assessment. And it works pretty well on these benchmark data sets, which are from SemiVal 2013, which are part of natural language inference and I think used in a variety of ways. So it's kind of old data, but a lot of educational question answer, written open-ended questions with answers. A lot of these, there's a lot of proprietary data out there that we can't get access to. And unfortunately, not a lot of open access data, but this is one of them. So SemiVal is divided into Beetle, which is all about electricity and electronics, 56 questions, 3,000 answers. And then science, which is 15 science domains, 197 questions, 10,000 answers. And these results, again, are on the augmented data where we use back translation to get new examples. And what we're showing is that SFRN plus, which is with BERT, is outperforming the state of the art on both unseen answers and unseen questions for two-way correctness, three-way correctness, and five-way correctness. But on science, which is more challenging, there's more data, but it's much more partitioned into different domains and questions. There's also this unseen domains task with the two-way, three-way, five-way. And SFRN is not beating the state of the art. And the state of the art, there's just one line there because it's kind of summarizing the best from different models for each class and so on. But it's still performing very well. And the way we want to use it for the middle school science questions is next year, we hope that we can actually integrate this for immediate feedback to students. But we haven't been doing that yet. And the collaborators on the project interested in education really want to understand the relationship between how students answer the questions and then how they do on the essays and how they're evolving as they're going through the whole curriculum. And so they want the evaluation of these 4,703 responses to do all that analysis. But they can't both do the analysis and do all the manual assessment. We don't have the resources. So that's where the human in the loop comes in. So they assessed 1,322 responses, 855, I think, with 2 annotators where we could get the interclass correlation coefficient, which is very high. And so we're going to try to do human in the loop on the remaining 3,381. Actually, you'll see, not exactly, but that's the basic idea. And so our proposed solution is to embed SFRN in this selective prediction system where we would look at the probability distribution over our 3 classes And if the max is not greater than some threshold level, then it goes to an expert. And why selective prediction? Well, there's a nice paper from last year at AAAI on how if you tell the human the model's best guess, or you tell the human the model's best guess and the probability, or you give the probability description or any other information, you're biasing the human. And the humans do a lot better, and the overall system gets higher accuracy if you just do selective prediction, which means that we can test it offline. We can have all the data labeled and simulate doing it with human in the loop, which is what we did. So we first try a heuristic policy where we pick a threshold probability. And why does that work? Well, there's been previous work that shows that softmax very often is a good confidence estimator. It's not always, and we actually have a model where it's not because the model's always confident. But sometimes it can be a very good confidence estimator. The question is, how well does it generalize? The answer to that, one piece of evidence for the answer to that will come in a moment. Another thing about picking a heuristic threshold is that how do we manage what people using this would really be interested in, which is, I want a certain level of accuracy and I only want to work this hard. So how do I manage that trade-off? And with a fixed threshold, that's not that easy to do. Or even like you have a bunch of thresholds on the shelf. It's just not that easy to manage it. So we wondered, could a more complex decision policy be learned? And that's what we try to do. So here's our data sets, and I'm showing you this big table mainly to show that there's the first coding, 855 examples where we had ICC. And then we have the second coding where the same annotators did the coding, but it was only one per item. So altogether we have, 1,300 or so, but it's kind of in 3 batches of a little over 400 each. And it also shows you the question difficulty for the students, because we've got the average score on the scale of 0, 1, 2 for each question. And the questions are designed to be a little bit more difficult within a lab. So we can see there's lab 1, 2, 3, 4, and 5. And then also more complex as the students go through the labs. The question difficulty for the students is not the same as the question difficulty for SFRN, and we actually use that as a feature on our model. So we've got this set of 855. That's not enough to train SFRN, is it? Well, no, but we do have 6,956 questions from the past, a decade of work that my collaborator had done that we could train SFRN on, and then just drop in little smidgens of the spring 22 data we're interested in doing to see how that improves things. And so this shows that if we don't use any of the new data, accuracy on the new data is really bad. And this is taking that first coding and dividing it into a train test set for SFRN. So that test set is the second half of the first coding. But if we just throw in 400 examples, we get up to 62% accuracy. A big boost, but not good enough, of course. So this just kind of shows why we picked 0.68 as our threshold probability, because it's showing on the graph for each threshold of the max probability class prediction, or actually for each class, we're looking at each class separately. So 2 is the correct, that's the green one. There's fewer of those. That's the smallest class. And then the other 2 classes, which are a little bit more equal in size, they intersect at around 0.68, and that's above 90% accuracy. But when we test this on our dev set, which is this set of 477, it gets an accuracy of 0.8, combining, pretending we're asking a human, but they already labeled it, versus letting the model do it. And the deferral rate, how much effort is the human doing? If they were actually doing it then would be 30%. So we're going to compare that heuristic policy to our learned logistic regression, which is using the SFRN correctness to be the labels of do we defer or not. And we use weighted cross entropy loss so that we can kind of try to emphasize accuracy more or less. Now, we can't manage the trade-off exactly, because we can't like sacrifice accuracy. Well, if accuracy goes up, human effort also goes up. They go up together. And the 5 features that we found were useful among, maybe a dozen that we looked at were SFRN's accuracy per question, which we treated as, the SFRN difficulty. And then the inverse of the proportion of the predicted class in the whole data set, and then the softmax probabilities. And so here, what we're seeing is we tested, a bunch of these, and for, 4 combinations of these 5 features, we can see the accuracy does go up and the deferral rate goes up. But this accuracy is not better than on the dev set with our threshold, but it's close, and the deferral rate is much lower. Plus, we have this weight parameter on our loss, where we can kind of control our emphasis on accuracy. So when we turn to our final test set, which is this test for the human in the loop system, the heuristic policy drops in both accuracy and deferral rate to below what people would like. Whereas with our learned policy, it generalizes better. The accuracy and deferral rates on the dev and test are a little bit more similar, but also, we can change our weight to emphasize accuracy a little less, 0.9 or more, and we have to bring it all the way up to 3.3 to get the same level of accuracy that we would get with humans doing all of it. And we've only reduced human effort down to now they're doing 65% of the data. But we're not done, because we're still working on a different way of learning a policy. Plus, now what we could do is take all the examples that have been labeled, train the deferral policy, and test it on all of our unlabeled data, and then selectively sample that when we're done to do the evaluation. So we might be able to do something that would actually be exactly what my collaborators want. So now I'm going to turn to my last topic for the day, which has to do with these undergraduate statistics questions, where there's a scenario and multiple questions for that scenario, and I'm going to talk about the recurrent relation network, which I think is pretty cool, but I especially think the contrastive learning part is cool, and hopefully you will too. So our goal here is, my interest in all of this is formative assessment, not summative assessment. In other words, how do we help the student learn more? We don't want to give them a grade necessarily. I don't care what grade they get. I don't know why this interests me, but it does. So with scaffolding on a per question basis, if they get the correct answer, you're done. You don't need to scaffold them anywhere. The whole course is scaffolding them somewhere, but not on that one question. If the answer is incorrect, it's kind of like there's nothing they said that you can build on to help them get to that next level. But if they're partially correct, you can. And how? Well, it turns out people in education research don't really know how. They just know that feedback helps, and they know it should be relevant. They should know it should be timely. But there's so many different kinds of assessment, so that there's no standard theoretical way to build the feedback. So we're all doing it together. We had 2 experts from this domain take 100 of the data set that had been reliably labeled and independently work to see, for this question too, how would they group the students into ones that get the same feedback? And I don't know if anyone's here is familiar with the old-fashioned terminology from decades ago when we did lots of manual annotation in NLP of clumpers and splitters. Okay, nobody here has heard it? Okay, so one person had 3 groups of feedback plus all the rest noise, none of the above. The other one had 15 groups. And when the 15 group person saw the 3 group, didn't see exactly what the groups were, but saw that there were only 3, it's like, oh, well, yeah, actually, I was being very fine-grained, and a bunch of them are related to each other. Let me go back and do hierarchical clustering on my clustering. So when we get that, then it becomes only 4 groups with the noise. None of the, doesn't fit into any group. And so then if we do a confusion matrix, we see that there's 43 out of 59 from this annotator, 43 out of 53 from this annotator. They give them the same feedback. Really good chunk out of the 100 responses. So if they could do that automatically, well, that really helps relieve the burden of giving students feedback. And then there's this other clump that's 21. So now we've got 64% where those students could maybe automatically get feedback, and all the rest maybe it would take more effort. I'm not sure what. Yes?
So this is just a very basic question about this. What is it? You said they're grouping the student responses. Are they grouping them by what kind of feedback they should get?
Yes.
What kind they did get?
No, they didn't get any feedback.
Yeah, okay.
So it's about, if I were giving feedback now, this is what I would do.
And is the clustering into 15 or 4 types by the content of the feedback or the
Yes.
style of feedback?
Content.
Okay.
Like,
okay.
how can I get the student to understand why they are only getting partial correct?
So this is very specific to the particular
Yes.
question too.
Yes.
It would be a totally different clustering. From
Yes.
question 3. Got it.
And
Okay.
different students, it could be totally different because they have different backgrounds. So maybe all your students, like in the physics curriculum, half the students come from the health sciences and half the students come from engineering, and they perform differently on their lab reports. So you would expect that kind of difference on answering questions about physics, that depending on their background, they may, different students might have different need for, understanding.
Meaning that's an open set of possible categories.
Yeah, so it's hard to do this in a supervised way, basically. There's no way to do it in a supervised way. So this is what a recurrent relational network looks like from a figure from this paper. And basically it's kind of like what I showed you before, except that we could have more nodes, and we could have all the nodes connected to each other, where each node's hidden state is updated with input from all the other nodes. But importantly, we can do this over multiple time steps to train this whole network. And that's kind of what we do. But we have context, text, the scenario, short paragraph. Then we have multiple questions for each one of these. Then we have the rubrics. Then we have the reference answers. So all of these would have text input that we would encode to become a node in this network. And then we have the student's answer. And we could connect them all together, but instead we decided, well, conceptually, we think it should be like this. And actually, I'm going to remove one of those graph layers in a moment, but that's the basic idea of our network, and over multiple time steps. But we also add in an answer state supernode. So this is sort of more what our network looks like, our answer state recurrent relational network, ASRRN. So we've got the context scenario at the top, then the questions underneath, then the rubrics and the reference answers, and then the student answers. And one of the things that's interesting was I asked my student, let's pretend that each question and its context goes by itself, and we don't have to have both questions together. Well, it turns out when the students see the scenario and then they answer the questions, they don't divide up their answer into, this is precisely the answer to the first question, and this is the answer to the second question. They kind of answer both questions distributed across both questions. So it turns out that we get better performance if we have both questions being considered while an answer to one of them is being assessed, if that makes sense. And then the super node is just getting information from all the other nodes, even though the other nodes are kind of structured to send information only in particular directions. And then after a certain number of time steps, we take the final state representation for the student answer and assess it. But in addition, where does the contrastive learning come in? Here. We want to learn a good representation of the student's answer so it can be classified correctly. But we decided to try to address this other goal so it could be located relatively closer to a distinct, useful, partially correct reference answer. So here are 3 partially correct reference answers, the RFP1, RFP2 for partially correct, and RFP3. And when we get that hidden state for answer 1, we want to classify its correctness, but we also want to see of the reference nodes, which does it have the max similarity to? Because if we can identify that, and we already know what that node represents because we've got the reference answer, then maybe that we just give them the feedback if that was the exact answer, the reference answer. And we're still trying to figure out how to assess that, but first we had to build the model that could even do that. And the way we do that is with contrastive learning, where the goal is to learn embeddings such that you've got similar sample pairs and you want them to all be relatively more similar to one another than they are to the dissimilar sample pairs. So like dogs versus cats. So there's a way that this would apply here, but we're making some very strong assumptions. The correct answers are homogeneous. There's one way to be correct. And maybe different ways to say it, but if it's correct, it's correct. That's kind of an oversimplification, but not too bad. Incorrect answers, heterogeneous. Well, that is totally the case, because sometimes the answer is not even relevant. But, you know, the educators and the assessors, the expert assessors, really do want to give the students partial credit. So if it's incorrect, it's just way off base. And you can imagine there's anything that's way off base, right? So there's many ways to be incorrect, heterogeneous. But partially correct answers, we're making the strong assumption that there's a partition of distinct ways to be partially correct. So I made up this goofy word, charisma genius. Charisma means partition, not charisma, but charisma. And we can see from that coincidence matrix or confusion matrix from the humans that that's not the case. There's a lot of noise, but we have to start somewhere. So that's what we're starting with. And so here's a very commonly used loss function for contrastive learning, where you're using a kind of recognizable loss function, but notice that in the numerator, you're summing over exponentiating of the similarity of each example to each example, training example xi, to the examples xj that are in the same, that are supposed to be similar. And that's temperature scaled. And then in the denominator, it's that term summed with the term that's summing over the similarity of the training example xi to all the xk that are in the class that's supposed to be dissimilar. And then similarity could be your favorite similarity function, temperature scaled so that large distances dominate when the temperature is high and small when the temperature is low, and so on. So we kind of modified this a little bit, and we have two types of numerators. One where we're taking our training example xi, and we have all the reference examples in the same class xj, xj1 to xjn, and we're getting the similarity temperature scaled of our training example to each one of those reference examples. And then we take the average. Because, like in the case of the correct answers, they're all supposed to mean the same thing anyway. Or the other numerator is, instead of the average over all of those comparisons of our training example to every one of the reference examples, we take the max. And then as we're training, it's going to get closer and closer to one of those. And then in the numerator, we're just using the summing over our training example similarity to the reference examples from the other classes, xk. So we got these two contrastive loss functions, L and L prime. And our ablation experiment, I'm not showing the full thing because too many numbers. I'm just showing that the sort of final result. But we tested with and without rubric nodes, reference nodes, super nodes, different combinations. And it turns out the rubric nodes do not help. So they're gone. And if we leave out all the nodes, we basically have something that's pretty similar to SFRN. But it turns out that the reference nodes help and the super node helps. And how many reference examples should we have for each class? Well, we got up to 4, and then we couldn't collect anymore. And 4 was better than 3, which is better than 2. How many time steps? Well, actually, we start to degrade performance if we do more than 2. And then with and without contrastive learning, it turns out that with contrastive learning, a whole different set of varieties of contrastive learning, it does better than without the contrastive learning. But the contrastive learning that works best is not the one I expected. I expected that we just wouldn't even use contrastive learning on the incorrect examples because they're all just noise. And I thought we had to have a noise node for the partially correct. But actually what turns out to work best is we have 4 partially correct reference answers that we ensure through collaboration with our educators. They're all distinct ways of being partially correct. They're not paraphrases of each other, and they clearly represent different degrees of approximating a correct answer, but not being quite there. So our best with contrastive loss uses this L prime for the partially correct, which is taking the max similarity node, and the average for correct and incorrect. And it's not the confidence interval around, and it's only 8 runs because we were running out of time. And these experiments are still being done. But so the confidence interval for ASRN with contrastive loss slightly overlaps ASRN without contrastive loss, but it's clearly doing something better. We compared it with large language model baselines where we encode the context, the question, the reference answer, and the answer, concatenate the 4 encodings, and then classify that. And both SFRN and ASRRN with contrastive learning way outperform these baselines. And ASRRN with contrastive learning way outperforms SFRN. Well, way out, it outperforms. And this is a visualization using t-SNE projection into 2 dimensions of the test set without contrastive loss on my right, your left, and with contrastive loss on the other side of the screen. And with the contrastive loss, we have bigger, fewer clumps, and within the clumps, less confusion among the 3 different colors, which are green for correct, blue for partially correct, and red for incorrect. So it's doing something. And it improves the classification performance, as well as getting us towards being able to identify, well, which way did you get this partially correct, so that we could give feedback. And that's the goal, because if we can do that, then the people who want to understand how to give feedback can study that on a larger scale. And how do we know whether this is really working? Well, we don't yet, but this is showing for the partially correct predictions to question 2B, where the accuracy on that question was only 82%, but it's still pretty good accuracy. There's 81 that were predicted to be partially correct, and for each one, we calculated which of the reference node representations is it most similar to, and 19 were most similar to 0, 54 were most similar to 1, and 8 were most similar to 2, and then reference node 3, nobody was similar to that. And this, what's shown in each cell is the average similarity over all n for this, it would be all 19, to that reference node. So the 19 are not all that similar to reference node 0, but we see that the 54 are very similar to reference node 1. I mean, that's like really high. I didn't expect to see similarities that high. And then these 8 are much more similar to reference node 2. So we do have a maximum similarity node for these 81 cases. We just don't know if that's what the educators would agree with, in part because then we'd have to get them to evaluate this clustering, and that itself is kind of complicated. So instead, what we're trying to set up with our new project is having them do more clustering so that we get different kinds of clustering outputs, and then measure the agreement between the humans on the clustering and our model on the clustering. But if you look at actual examples, a lot of them, if we cherry pick some, they look pretty good. So here's an example that we actually used as a correct reference answer that 2 experts agreed on. You could compare the average length of each of their catches and their fishing habits. The one with more and larger fish is the better fisherman. And this was in the context of asking students, here's a scenario. If I want to know if somebody's a better fisherman, would I use statistical reasoning? And if so, how would I do it? So this is answering the second part. And ASRN agreement on predicting that the student got the correct answer, and which, the student got the correct answer and that it should be similar to one of the reference answers. Here's two, and again, we're using the average. So it's sort of each correct student answer is kind of equally similar to all the reference answers. But you can see that the students are articulating this in kind of different ways and with different numbers of sentences. One is very terse, the other is a lot more verbose, but it's basically all the same idea. And then here, A and B agree with each other, but on a totally different thing than ASRRN decides. And you can see that this is, there's this student kind of doesn't quite get it. Using data from the fishing trip, I would plot the data using a scatter plot of the lengths of the fish that each brother caught, and then run a significance test to see if it is a significant difference. I like the scatter plot idea. I love scatter plots, but which significance test of what measure, so the students kind of throwing out words, right? Well, then, oh, I forgot. So let's compare it to a GLM, Gargantuan Language Model. Because I don't know how your students are feeling, but a lot of my students are feeling like, I can't do my research anymore because I can't beat, ChatGPT or GPT-3 or GPT-10, So we tried few shot prompting on this data set with GPT 3.5, where what we're giving as a prompt is a context, the question context. Then we say, you've got to evaluate the correctness of the following answers based on the context and the examples provided. And then we give the question, because there's two different questions for each context, and we give the student answer. And then we say what our evaluation of that student answer would be. Correct, the answer is correct because blah, 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 blah. And then we have different prompts for correct, partially correct, and incorrect. And that's what we gave to GPT 3.5 with our test set. And here's the results with 0 shot, 1 shot, and 9 shot. And so ASRN outperforms. So my PhD student is like, okay. But another kind of thing that I think is interesting is that the variance is higher with GPT than it is with ASRN across the questions. And also the question difficulty is not the same as the question difficulty that would be like a human's question difficulty. So not only is ASRN outperforming in terms of total accuracy, ASRN has more similar accuracy on the questions, except for question 3A and question 4B. Is it 3A and 4B? Or 3B and 4B, where the accuracy is really high. But still, if you measured the variance, you would see it's less. I should have put that in there. Oh, and I have a column there I didn't fill in. Anyway, sorry about that. And the question difficulty, accuracy as a reflection of question difficulty ordering is very diverse across the different shots. And again, there's just more variance. So I think that's, oh yeah, I wanted to end with some, oh, thank you so much for your attention all the way through this long talk. My current work in open questions, I'm really excited about looking further into human in the loop. And so what we're trying to do is jointly optimize for high accuracy and low deferral rate in selective prediction. So we're trying joint training of a classifier and a deferral policy, where the deferral policy is actually using learned representations. And we're kind of getting somewhere, but we're not there yet. And then I do have a student who's working on applying rubrics, analytic rubrics on this wide scale to long form text, namely lab reports, where we treat each rubric dimension as a query whose answer is the most relevant sentence. And we have to scale the answers on this 0 to 5 point scale. So we're using ordinal log loss, where the difference between the truth is 5 and the model predicts 4 is less bad than if the model predicted 2. Then as we make progress on that, we could actually apply that kind of a model to even middle school student essays, where we have a much simpler kind of rubric, but where we wouldn't have to have reference text and kind of iterate over our pyramid and blah, blah, blah. So open questions that I'm interested in continuing to investigate are just ways to constrain vector space for more precise representation learning. So we, in the projects here, the proposition is a very important unit. And so that's why I put use of prototypical propositions to anchor relevant locations in vector space. But, I'm kind of interested in trying to pursue that further so that we can try to take charge back from the learned representations and try to understand what they're doing by forcing them to do what we want them to do. And then also multitask representation learning for both short and long form student writing, because right now we have different tools that do the assessment of the short form and the long form. So we can't relate them because the learned representations don't relate. But if we had some kind of multitask learning, maybe we could actually give students feedback. So this is really long range, but well, you should have gotten this stated in your essay a little bit better because I noticed you got this question right. So go back and think about why you answered the question that way, that kind of thing. So those are my things that I'm thinking about now. And here's a bunch of publications ordered by date if you're interested. And thank you for your attention. That's it. Then.
Great, thanks. Just excited if you're able to make progress in that data release. That would be really and surprising.
Yeah, the ones that we're collecting now and next year, I think we'll be able to release, but only after the project is over.
But I was wondering on the final slide about propositional anchoring, which then links back to your discussions of pyramid on clause extraction. So I'm wondering what your current thoughts are on what it means to extract a proposition grounded in text. So I guess historically it would have been technical parser.
Oh, well, we actually have a neural model that does that.
Now we have things, but
yeah, now, yeah.
Right.
So what is the nature of your question again? Like, could we do that?
Like how accurately, like how happy are you with your current ability to isolate a section of text and say that's the proposition?
Using the old style stuff.
You're using like anything.
Using anything. Oh, well, okay. So one of my former students developed a neural architecture that actually required pre-processing with dependency parsers of the sentences. And we had collected a data set where we asked human annotators to find the clauses. And so we had a data set, I think, of 30,000 human annotations. And what there was a lot of work around that same time on using Wikipedia edits and other kinds of like sort of free out there in the wild bracketings of clauses within sentences, or relating a full sentence to multiple simpler sentences that have the same meaning. And the data was very noisy, so I sort of felt like, well, yeah, sure, we can do it if we have an annotation. It's getting the annotation that's hard. And there's different kinds of annotation you might want, because what I'm focusing on tensed clauses here, but we've got untensed clause, we've got different things that we might like, noun phrases that have all the semantic structure of a clause. So it sort of depends on what you want to call a clause, but I do think propositional content and how propositions relate to one another is something I've always been interested in. And that's a natural fit for students learning to articulate their thoughts in education, because it's all about trying to assess what they know and their understanding, which is about their ideas and propositions.
And this 30,000 element annotation, that was noisy?
No, that wasn't that noisy, but it was very specifically tensed clauses. And other people have collected similar data sets, and it's, diverse kinds of clauses. Finite and non-finite clauses, and sometimes noun phrases that are propositional. And so, there's no single annotation standard. And then a lot of the data that people were testing neural architecture architecture, Sean, wasn't actually human annotated. It was just Wikipedia edits where, or text simplification kinds of contexts where here's, like stuff where you have a text that's rewritten for a student at a less advanced educational level. And you can get parallel texts of, here's a complex sentence with multiple clauses and a complicated syntactic construction. And then here's a rewrite into 3 simple atomic sentences. And people would train on that kind of data. But that kind of data is noisy because it wasn't created for the purpose of finding what are the propositional units, however you want to define that. But I think if we have that annotation, sure, we can do it. It's not that hard. It's because if it's supervised, it's, any other questions? Well,
I'll ask one that other people should ask. I'm going to ask something out of left field, if that's
sure.
I think the work that you're talking about here is all on relatively small but high quality data sets. So sort of direct supervision. And I'm thinking about all the excitement about MOOCs 10 or 15 years ago, and how you could collect lots of data about what lots of students were doing, but then you'd be in a more unsupervised realm. Maybe you'd have some pure grading, but that would be low quality. Maybe you are collecting things like reaction time, which gives you some indirect indicator of where people are struggling, or maybe just how often they need to use the bathroom. It's hard to tell. Do you think there are opportunities for fusing this kind of work with larger scale data, at least for curricula which are where you have tens of thousands of students using the same answering the same questions?
I was with you until answering the same questions because of our concerns about plagiarism and everything. And is the student really producing their own genuine answer, or are they looking it up?
Well, let's say
that's not an issue. Yeah, sure. I definitely think so. And I think, the AI ed community is kind of smallish, and they're very interested in becoming bigger and more visible. And so I think there's a huge amount of opportunity. Yeah, I think there's a huge opportunity here for kind of team science, where we have, actually Sanjeev and I were talking about some of the things he's interested in, and people asking him to look at classroom discussion data and how difficult that is when the students are all talking at the same time and so on. But that's a very high interest area for some people. I was mentioning Caroline Penstein-Rosé's work on computer supported collaborative learning, and she's really interested in that kind of thing. So I think it's sort of right for, if we could get the right people together, then they could do something at greater scale, and it wouldn't have to be this kind of high precision, small data set for one curriculum. And in fact, with the statistics project that just got funded, the goal is to work with these partner institutions where some of the questions are actually questions that are highly curated, and others are questions that each institution would submit. And so we get a great diversity of statistics questions for introductory statistics. And we're trying to move that along that way. But I think, there's a lot of opportunity for that. Thank you.
Becky,